So now that we've mastered solving one-step, two-step, and multi-step equations, we're going to take a look in Chapter 3 at different ways to use equations. So Section 3.1 deals with solving literal equations. So a literal equation is going to have more than one variable. If you looked up the word literal in the dictionary, literal is actually derived from the word letter, so that's why it means that there are more than one letter in these literal equations. So we're basically doing the same thing we've been doing. Now we might not be doing quite as much math, I guess you could say, because we're not actually calculating anything. We're going to leave all these letters. So when we are simplifying this equation, the first thing we need to do is to get rid of the parentheses. So we're going to have P equals 2L plus 2W. We want to get L all by itself. Remember, we're solving for the variable L. So now we have a 2 times L plus 2W. So we're going to subtract 2W from each side. So we end up with P minus 2W equals 2L. And then we have 2 times L. So we want to go ahead and divide by the 2 to get the L all by itself. We end up with L equals this whole thing right here, P minus 2W over 2. We're going to use the same literal equation here. This time we're going to solve for W. So same sort of idea here. I'll go over to the side so it doesn't overlap when I advance the slide. So it ends up being P equals 2L plus 2W. Again, we're just distributing to get rid of those parentheses. This time we're trying to get W all by itself, so we're going to take P minus 2L equals 2W. And now we'll go ahead and divide by 2. So we end up with W equals P minus 2L over 2. So in many ways, this is exactly like we were doing before, except, before we were actually subtracting something, subtracting a value, or we were actually dividing by a value, where here we're just leaving all of the letters. They're just ending up in a different order until we actually have values to substitute in for them. So it says, write a formula that states when you can, and state when you can use it. Explain what each letter in the formula represents. So for instance, we have done area equals length times width. And if we wanted to say, okay, well, I know the area and I know the width, but what's the length? We'd say, well, how can we solve for length? We could say that, well, we could divide by W on both sides, and we could say that length would equal area over width. That's what they're talking about here. We're writing a formula. We're saying this is the area, the length, and the width. We don't know these values yet, but once they tell us our area and our width, now we'll be able to find our length by just dividing those two, by just manipulating this literal equation a little bit. So in your notes, a literal equation contains several variables. So before we were just using one, this one has several variables. It can be solved for one of its variables using techniques similar to those you learned for solving equations with one variable. So these are just like the example we just did with the P's and 2's and the L's and all that. So for example 1, we want to solve for H. Well, H is being divided by something. So the first thing we're going to have to do is multiply by that something to get rid of it. So our first step is going to be multiplying each side by L. So that cancels out our L's. And now we have LF equals WH. Now we're still trying to get H all by itself. Sometimes it helps when you find out, okay, for H, just go ahead and circle your variable that you're solving for the whole way throughout so that you can keep an eye on it. And then also read these out loud when you're just getting used to them. So you can say W times H divided by L, or W times H. Now we know that we have to divide by W to get rid of that W and get H all by itself. So now our w's cancel, and we're left with this LF equals W equals H. There's our H again. Now it's all by itself, so we know that H equals LF over W. And remember, we always want to start with the variable that we're solving for when we give our answer. So it just ends up being H equals LF over W. We just flip-flop that around. Example 2, this is like the one we just did. So let's go through the motions here on it. For L, so we're going to get L all by itself. The first thing we're going to do is subtract 2W from each side. We end up with P minus 2W equals 2L. And then divide by 2 on both sides. So we end up with L equals P minus 2W. Then if you're following along example 2 in your book, it says now evaluate when P equals 58 and W equals 6. So now we're still finding the length, and it's going to be easier actually to substitute the values in now than it would have been if we did it at the very beginning, because there's less math involved. We just have it down to the very final step and we can put those values in. So we said find L when P equals 58, so we just have to find our P's and put in 58. And then W equals 6, we just find our W and put in 6. And we can just follow our order of operations. So we want to go ahead, remember anytime you have an expression in your numerator that's kind of in parentheses, you have to do everything inside of those first. So we would have 2 times 6 is 12, 58 minus 12 is 46. So we have 46 over 2, and when we divide 46 divided by 2, we get L equals 23. So there we were able to do the math in more of a simple step, rather than shifting these numbers all back and forth all over the place and worrying about if we made a mathematical error, instead of just the way we just did it, which was just moving the letters around, or our variables around. So the distributive property is often an important step in solving literal equations. So it says, for example 3, which is at the top of page 95, solve ax minus 5b equals 7x plus 18b for x. First things first, we notice that our x's are on opposite sides. So sometimes it might help if you draw a line down so you can see, oh, this is one side, that's the other. We have to get all our x's together. So first things first, we'll just subtract our 7x over here and move it to the left. So we'll also subtract 7x on this side. Whoops, wrong direction. So we're left with ax minus 5b, which is what we had, minus 7x equals 18b. Now we might as well go ahead and put the b's on the other side, so we'll go ahead and add 5b and add 5b. So we have ax minus 7x, and then when we have 18b and 5b, remember b and b, that's like terms, so we can just add our 18 and 5, we get 23b. Now, ax minus 7x equals 23b. We can't exactly subtract 7 from a to combine like terms with these x's here, because we have another variable involved. So we're going to kind of do a reverse distributive property. Remember, if we had like x times 2 minus 3, we'd end up with 2x minus 3x. That would be distributing our x's into those numbers. Now we're going to kind of say, oh, well, there's an x here and an x here, so I can actually pull those out. So now I can say x is the common variable. Do that over to the side here. So we say x, and what am I left with? Well, I'm left with an a minus 7. And I can say that the quantity a minus 7 times x is equal to 23b. Then we're still trying to get x all by itself. Remember, that's our goal. We're solving for x. So the last thing I'm doing, well, if I have the quantity of a minus 7 times x, I can divide by that quantity of a minus 7. Oops, that's a minus sign. And that's going to get x all by itself for me. So now I'm going to say divided by a minus 7. So I have x equals 23b divided by a minus 7. And that's how I get x all by itself. So solving literal equations, I'd go ahead and put this in your notes. These are the steps. So solve using the distributive property, clear the equation of fractions by multiplying both sides by the least common denominator, which we did towards the end of chapter 2. Simplify both sides of the equation. Collect all terms containing the desired variables on one side of the equation, on all other terms on the other side. So like we got all the x's on one side, everything else on the other for that last one. Use the distributive property to isolate the desired variable. So that was kind of like I said, the reversed distributive property. We were pulling out that x and multiplying it by the quantity. And then divide both sides by the coefficient of the variable. That just means the thing that it was being multiplied by. So example 4, which is on the bottom of page 95. So we have solve a plus 2b equals, or over c equals cd minus a over b. And it doesn't say that here, but we are solving this for a. So first things first, we have denominators, and we want to go ahead and get rid of those. So what's our common denominator? Well, if I have a c and a b, just think about it. What if I had a 2 and a 3? What would my common denominator be? I'd multiply by 6. Well, how did I get that? I multiplied the 2 times the 3, right, to get the 6. So in this case, I would multiply my c times my b to find our least common multiple. So I'm going to multiply both sides by bc. So on this side, our c's will cancel. On the other side, our b's will cancel. And we're left with what's on the top, because this kind of became a 1 on the bottom. So now we just have b times. So we have our b times the quantity of a plus 2b, and we have c times the quantity of cd minus a. Then we need to go ahead and distribute to get rid of our parentheses. So we have a times b would be ab plus, well, b times 2b would be 2b squared. C times c and c squared and the d minus ac. So that's our next step. I'm going to go ahead and continue this on the next page. So remember, we're still solving for a. So now I notice that my a's are on opposite sides. So I'm going to go ahead and add a c on this side so that I can add it on this side. I have ab plus that my ac plus 2b equals c squared d. Next, I want to get all my other variables on the other side. So any terms that don't contain my a are going to move on over. So I'm going to subtract 2b squared. I'm left with a plus ac equals c squared d minus 2b squared. Now I'm still trying to get a all by itself. So here I'm seeing, oh, well, I can kind of do that reverse distributive property. I can pull that a out. So it'd be like I'm taking my a times a b plus a c. So I have b plus c times a equals c squared d minus 2b squared. Our very last step then is to get this a all by itself is to just divide by b plus c. And when I do that, I get a equals 2 squared d minus 2b squared over b plus c. Now, don't get intimidated by all these letters floating around. Just remember, we're doing the same exact steps we were doing before, except now instead of seeing numbers, we are only seeing letters, which means our letters really start to pile up in the end because we're not, before we would have a 2 and a 3 and we would combine those and have a 6. We just had one digit instead of two things. Well, now we just have all letters and we can't, not all letters, but mostly letters, so we can't actually combine those things into something like a 6. So don't get intimidated, just remember these will start to kind of stack up, but we're doing the same process. So the manipulation of literal equations occurs in many disciplines. At the top of page 96, it talks about different scientific fields and things like that. But I even use this when I'm at the grocery store and I'm just trying to find out price per ounce on laundry detergent to make sure I'm getting the best price or the best deal or value for my money. I use basic literal equation concepts of manipulating what I know and what I don't know and solving for an unknown variable such as price per ounce. So the last thing we're going to look at with literal equations is something called a subscript. So subscripted variables, such as r with that little 1 and r with a little 2, are often used to clarify the meaning of formulas. So just a refresher on subscripts from English class, this little number here, that's a subscript. It means it's written down smaller, and it's telling us that's the rate of one or the rate of the second one. So these are treated just like other variables. So it doesn't assign any value to it other than it's the first one we're talking about in the problem and the second one we're talking about in the problem. So if we look at example 5, it says the boiling point of an ethanol solution, B of, oh goodness, I need new glasses, B of S, rises as sugar is added according to the formula B of S is equal to B of E plus KEM, where BE is the boiling point of pure ethanol. Solve the formula for M. Then find the molality, I can't pronounce that word, M of a solution that has a boiling point B of S of, and then give some values for us. First things first, we have our formula. We just want to identify so we know what they're talking about. So B of S is, or I shouldn't say B of S, I guess, but just BS is the boiling point of the ethanol solution, or the solution. E is the pure ethanol, and KE is our constant. And M is that word that I can't pronounce of the solution. So all we need to do is go ahead and solve, first off, for what they're giving us. So it says solve the formula for M. So first things first, this looks like a two-step equation to me. I'm adding and I'm adding or subtracting and then multiplying or dividing. So I will have to subtract the BE value from both sides. And then I still want to get M all by itself, so I'm just going to divide by KE. Now I'm left with M equals BS minus BE over KE. And then we can go ahead and substitute in our values. So they said this value was 82.37. This value is 78.26. And KE is 1.22. So we would just take those and substitute them in. So we would have 82.37 minus 78.26 all over 1.22. And when we plug those numbers into our calculator, do this first, then divide by 1.22, we get M equals approximately, or approximate squiggles, 3.37. So that's it for this lesson. Go ahead and take a look at your assignment and let me know if you have any questions.